Hello, welcome to Econometrics Melody. In this video, we will discuss about the matrix derivative, how do we calculate the derivative of the expressions involving matrix. In our earlier video, we had seen that the matrix notation of linear regression equation, this is given by y is equal to xb plus e, where y is our dependent variable and our x, this is the independent variable. This is the matrix, it contains independent variable, and e is our error term. So we need to estimate the value of beta such that we tend to minimize the error. Our error, it can be written as y minus xb. Now we need to estimate the beta, and our optimization function, in this case we tend to minimize the sum of the square of the error. So this is the matrix notation or the vector notation to represent the sum of the square of the errors. And for the optimization problem, and in this particular case minimization of the sum of the square of the errors, we need to follow these procedures. First of all, we calculate the first order derivative and we set it to 0 and calculate the value of x, and we calculate the second order derivative. If the second order derivative is positive, then we conclude that the function is minimized by this value of x, and if the second order derivative is negative, then we conclude that the function is maximized by the value of x attained when we set first order derivative to 0. If x is a matrix, now we need to operate this maximum optimization problem making use of derivatives in matrix. Now let us explore that by the help of two examples. So here y is equal to, there are two equations. Actually we are trying to mimic the situation of linear regression equation, and we have taken only two equations, and making use of matrix multiplication we segregate it into matrix as well as the vector. This vector is our variable beta1 and beta2, and we have the first independent variable and its value is 2, 6, and the second independent variable, its value is 3, 8, and we name this matrix by A, and the vector or variable we name it as B. Therefore this expression can be written as y is equal to AB. So where we have a convention of representing the column vector or denoting the column vector by simply the alphabet, so here we have represented it by B, and the row vector we represent it in terms of its transpose. So let us take the derivative of y with respect to beta transpose, because it will be convenient for us to represent the information in a more systematic way. Now let us take the derivative of these two equations first with respect to beta1 and collect their coefficient. The derivative of twice beta1 with respect to beta1, this is simply 2, and we don't have beta1 here. So in the second equation we have beta1 over here, so we get the coefficient as 6, and we don't have beta1 here. So we are done with taking the derivative of y with respect to beta1, and we present the coefficient following the order of this vector, that is beta transpose. So the coefficients after taking the derivative with respect to beta1, we have placed it in our first column. Now let us take the derivative of these two equations with respect to beta2 and write the coefficients in the second column. Here we don't have beta2, here we have beta2, and the derivative of 3 beta2 with respect to beta2 is simply 3, and the derivative in the second equation. So therefore derivative of y with respect to derivative of beta transpose, we get it as 2, 6, 3, 8, and if we compare it with our initial expression, we had supposed this to be A and this to be vector B, so the result is simply A. Therefore this was equal to derivative of AB with respect to derivative of beta transpose, and we got it as A. Because in our example we have represented these two equations as AB, and that was equal to y. So y is equal to AB, and we took the derivative of y with respect to beta transpose, and the result was A. And similarly, if we follow the suit, if we could take the derivative with respect to beta, then the result would be simply A transpose. And later we will develop this rule that if the variable with respect to which we are taking the derivative, if they are transposed to each other, then we simply take either the pre-multiplication or the post-multiplication term, and if the variable with respect to which we are taking derivative, if they are same, then we take the transpose of the pre-multiplication or post-multiplication term. Actually, we want to develop this understanding, and let us see another example, and further we will solidify this understanding. So generally for the column vector, we denote it in a simple alphabetical notation, while for the row vector we represent it as the transpose. So we have B vector. B is beta 1 and beta 2, and its transpose is represented in its row form. And we have a matrix A is 4 7 6 9. So out of this we are going to construct a quadratic equation, and here B is treated as variable because we don't know it. Y is equal to beta transpose and A and B. First of all, let us operate it and find the quadratic equation, then after we'll take the derivative. So if we operate a simple matrix multiplication, this is equal to 4 beta 1 plus 7 beta 2, and then 6 beta 1 plus 9 beta 2. And after we are left with beta 1 and beta 2. Now let us again multiply it. So this is equal to beta 1 and then plus beta 2. We are assuming that we know the matrix multiplication. Now let us again multiply it, and which further this is equal to beta transpose AB. This is our matrix notation. Now let us take the derivative with respect to beta. So this is equal to, beta is generally column vector, beta 1 beta 2. Now we'll take the derivative of this y in the numerator with respect to beta 1 and beta 2, and we will write the result in this form, that is in the form of column vector. So first of all, we are going to take the derivative of y with respect to beta 1, and let me do it a bit directly. Now let us take the derivative of this y again with respect to beta 2 and write in the second row. So let me write the value of matrix A. Now let me divide this 8 into two equal parts. So this is 4 beta 1 plus 4 beta 1 plus, and we have 18. So let me divide it into two equal parts, 9 beta 2 plus 9 beta 2. Now let me arrange it according to our requirement, actually in the form of this matrix. Now let us again split them according to our requirements, and we're going to separate this matrix with the other. And so this is the result. Now let us segregate the constant and the variable. So we are left with a simple matrix multiplication plus, and let us follow the suite in this case as well. If we compare the result, this matrix with matrix A, then this is simply 4 7 6 9, our matrix A, and beta 1 and beta 2. So the column vector of beta 1 and beta 2, this is simply our vector beta plus. And if we compare the result again with matrix A, so this is simply A transpose, and here again we have B. So this was our derivative of y with respect to of derivative of beta, and our y was equal to derivative of beta transpose A beta with respect to derivative of beta, and we got this result. And if A is symmetric, then A transpose and A would be equal. So in case of symmetric A, this would be equal to, let me show the result. So y was equal to AB, and we took the derivative of y with respect to derivative of beta transpose, and the final result was A. Similarly, the derivative of y with respect to beta, we got this result, derivative of y with respect to beta, that is derivative of beta transpose AB with respect to derivative of beta, is AB plus A transpose B, where A is not symmetric. Had A been symmetric, then in that case A and A transpose would be equal, and we would have twice AB. Let me again write this result. So the first result, it was in case of the linear form, and the second result, it was the case of the quadratic form. So we took y as now. Based on this result, we want to propose a simple rule for our understanding, and we will apply this rule in order to find the OLS beta estimate in our next video. So let us begin with the first example. then in that case we compare the variable in the numerator and denominator. Here b is our variable, and if the variable in the numerator and the variable in the denominator are transposed to each other, then the pre-multiplication term or the post-multiplication term, we take it the way it is. So this is the rule we want to have a common understanding on, and which is true by this example or the evidence as well. And derivative of y with respect to derivative of beta. If this operation was possible, then as the variables in the numerator and denominator, they have the same order, that is, they are not transposed to each other. In that case, we will take the transpose of either the pre-multiplication or the post-multiplication term. So this is the understanding that we want to develop. Once again, if the variable in the numerator and the variable in the denominator are transposed to each other, we take the pre-multiplication or the post-multiplication term the way it is in its original form. And in the contrary, if the variables they are in their same order, then we take the transpose of either the pre-multiplication or the post-multiplication term. And let us see if this rule applies for this second case, for the quadratic form or not. And we are taking derivative with respect to b, so we have 2b over here, so we apply the product rule. Let us consider beta transpose as the variable, then this entire term ab, it acts as the constant. And if we compare it, the variable in the numerator and the variable in the denominator are transposed to each other. We take either the pre-multiplication or the post-multiplication term without changing its order. So this is ab plus. Now we are done with this. Now let us consider this b is our variable, therefore beta transpose a, so this is going to act as a constant. Now if we compare beta in numerator and the beta in the denominator, they have same order. So in that case, we take the transpose of either the pre-multiplication or the post-multiplication term. So here, according to our rule, we need to take the transpose of the pre-multiplication term. And if we operate it, we get it as ab plus, and the value of ab transpose, this is equal to b transpose a transpose. We get the result as a transpose, and the transpose of the transpose is the variable itself. So this is our final result. And as x is our variable and we compare it with the numerator and denominator, as they are of the same order, we take the transpose of either the post multiplication or the pre-multiplication term. If this derivative is possible, then this should be our result. Now we compare the variable. The variable in the numerator and the variable in the denominator are transposed to each other. We write the pre-multiplication term in its original form in the same order. So we have 2x in our numerator, so we are going to apply the product rule. So dy by dx in that case would be equal to, first of all, let us consider x transpose is our variable, then this is our post multiplication term. So once we compare this, the variable in the numerator and the variable in the denominator are transposed to each other. So we write the post multiplication term without changing its order. Plus, now let us consider this x is the variable and this x transpose a, this is our pre-multiplication term. If we compare the variable in the numerator with the variable in the denominator, so they are in the same order, in that case we need to take the transpose of the pre-multiplication term. Now let us see a simple example behind the logic of the product rule. Here it seems like we are taking the derivative 2 times. So let us see a simple explanation. Product rule is basically finding the change in the product of x, y. So let us take a rectangle. Here the length is represented by x and the width it is represented by y. And let us take a very small change in x as well as y. So this is our small change in x, and let us take a small change in y, and let us complete the new rectangle. So due to the change in x and y, the area of this part x into change in y, and the area of this new rectangle, this is given by y change in x small rectangle. This is given age, the area is given age change in x into change in y, and age both the change in x and y, they are very small. The product of this small term is nearly equal to 0, or we can call it is the error term. So finally we had xy and we made a small change in both x and y, and the result of the change, this is equal to x into change in y plus y into change in x. So this rectangle, it represents x into change in y, and this rectangle, it represents y into change in x, and the small rectangle, the area is negligible, and therefore we say that change in xy is equal to x change in y. So this new rectangle at the bottom, x into change y plus y into change in x, this rectangle, new rectangle at the right, and this small rectangle with the dimension change in x and change in y, it is nearly 0. So this is the logic behind the product rule. So a final review before we call it a day is the variables, they have same order. The pre-multiplication or the post-multiplication term, we take the transpose of it. The variable in the numerator and the variable in the denominator are transposed to each other, so we don't change the order of either the pre-multiplication or the post-multiplication term. And if taking derivative in this order is possible, we use this relationship. Similarly, for the quadratic form, in that case, we first of all we concentrate, this is x transpose is our variable. The variable in the numerator and the variable in the denominator are transposed to each other. We write the post multiplication term without changing its order, plus, and now we concentrate with this x and consider the remaining is pre-multiplication term, and in this case is the order of the variables, they are same. Then we take the transpose of the pre-multiplication term, and if we solve it, this is simply equal to a transpose x. Taking derivative with respect to its transpose, if it was possible, then we would apply the same rule. First we consider this is our variable, so and we compare it with the denominator. Is they have the same order, we take the transpose of the post multiplication term plus the product rule. Now we consider this is our variable, and we take the entire term in the left is our pre-multiplication term. The variable in the numerator and the variable in the denominator are transposed to each other. In that case, we don't change the order of the pre-multiplication term. So if taking derivative in this order was possible, then the result would be this, and if taking derivative in this order was possible, then we would get this result, and we have proved this by the help of example as well. And if taking derivative in this order was possible, then the derivative would be this, and if taking derivative in this order was possible, then we will get this result, and we have seen this by the help of our example as well. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics, Melody.